So now let's take these rays or wavefronts or particles and have them interact with another material, right. So they start off by propagating either in a vacuum or through air, which we might consider to be almost like a vacuum, and then let's think about what happens when the waves interact with some kind of medium. They hit a medium that's different. So what's going to happen essentially is that we use materials to bend rays or alter the wavefronts, if you like, because they're obviously very closely intertwined. So I take some kind of material, let's see, you just draw a rectangular block of material. So we have some kind of material, and then we start up here and we send our light rays on their way. And let's talk about the different things that can happen. So I'm going to mention 4 different cases. One of them is that light comes around here to the corner and then starts to bend around the corner. What is that called? So diffraction, right? So here's another case, and this one will be the most important for optical systems. The light comes along, then its course is bent in some way. Say maybe I'll draw like this and then back out. So hopefully that looked like it was bending. Maybe I didn't put enough bend into it. It should not look like it's going straight through. Make it a little more, let me do the whole thing over again. So we'll go here, put some obvious bend into it, and come out like that. So we have some kind of bending going on. This is the case of transmission of the light through the material, through the medium. So this is transmission, and the bending of the rays is called refraction. Refraction of the rays. Another thing that can happen the light could come into the material and just kind of, and let's say the light comes into the material and never comes out again. So just absorption. So the light is lost forever. Probably the material would heat up then, right? Heat is usually the ultimate place where energy gets kind of lost, or the final form for it, let's say. So this part is called absorption. It's something important to keep in mind. The more materials, the thicker they are, the more materials you put into your optical system, the more you'll be just losing some light, right? What case remains? What else can happen to the light? Reflects away, right? So if this surface happened to be a shiny mirror, then we get reflection. So comes down like this. Angle of incidence should be equal to the angle of reflection, right? So this angle and this angle should be the same. And off the ray goes. So this is reflection. So let's talk about a couple of these in a little bit of detail. Mainly I'm going to be interested in refraction today. But for reflection I should say a little bit about it. I've drawn one kind of reflection there. This kind of reflection where these two angles are the same is called specular There's another kind of reflection. Just kind of redraw the material here, where let's say rays come in, but they may go in what seems to be various random directions. All right, so they bounce in all different sorts of ways, and this is called diffuse. Right. So these are two kinds of reflection, and these become extremely important in computer graphics for rendering. So when you want to model surfaces, do they look shiny like a mirror? You have the specular case. Does it look like, let's say, the carpet on the floor here? Then this would be more of a diffuse case, right? You cannot look down on the carpet and see your face on it, right? So it's diffusing the light all over the place. It doesn't look completely dark, so light is clearly bouncing from it, but it's diffuse. And now, what's the most important law for refraction between two materials? Snell's law, right? So Snell's law is the basic expression. I have Snell's law, which is N1 sine theta 1 equals N2 sine theta 2, which I guess is meaningless until I make a picture. So I have two different materials. I have an upper material and a lower material, and which one is air and which one is, say, a piece of glass. One could be water, one could be air, all sorts of possibilities, right? You've noticed that a swimming pool can act like a lens sometimes, right, and you get very interesting effects from that. So any two materials coming together, and now we draw a perpendicular line. So these are two materials. Let's say material 1, material 2. Draw a perpendicular line. And now we have the light ray coming into the boundary. And then the light ray leaving. Now I mark my angles here. Theta 1, theta 2. These are both meant to be positive angles, so whichever way you. And I guess I haven't fulfilled the formula here in terms of putting in all of the components and defining them. So the ends, I'll put n sub I is equal to c, the speed of light in a vacuum, over the speed of light in the medium. So I'll put in medium I, since I've numbered my materials or media. So sorry, I've changed the words a bit. Material or medium. Be a little more consistent. Medium 1, medium 2. So n sub I is called the refractive index. And note that by the time you're done here, what really matters at this interface is not the absolute value of the refractive index, but what matters is the difference between the two refractive indices, correct? Let me just give some kind of simple qualitative examples that correspond to the algebra here if you were to put these things in practice. So if I have a fast material and a slow material, and the light ray is coming down, try to make it look like it's about 45 degrees. What should happen to it? The waves are going to be propagating more slowly in the slow material, so that causes it to bend upward or downward? Is that right? Down or up? Let's see. I'm going to have to actually go and do the calculations. That seems interesting. Fast material, slow material, wave fronts. Ah, yeah, sorry, thank you. It's down. Yeah, okay, good. I have a mistake here, but I see. So, all right. So we goes downward. So we draw a straight line through here, and downward we go. Yep. I sometimes like to think of a kind of army marching along, right, and then it slows down. The waves get closer together, but if you actually look at the normals, right, which is the wave fronts, then it propagates downward. That's right. So it's an interesting, when I sort of think about it, imagine like a marching band coming along, but then they get slowed down, they get compacted together, but yes, the direction of the ray then ends up as perpendicular to the wave front, ends up pointing more downward. If we go the other direction, slow to fast, again at 45 degrees. So in this case, should be the opposite, I hope, right? What do you think? So I draw the rays through here and should come off like this. A couple more qualitative things and then we'll start talking about lenses. So let's go back to the fast, slow case. And if the ray of light is very close to perpendicular, then when it leaves, it's going to remain very close to perpendicular, right? So the amount of bending is not very much for a close to perpendicular ray, right? That's close to the perpendicular to this boundary between the two media. So that's just something to pay attention to. So when a ray of light goes straight in, or the wave fronts come right in parallel to the surface, to this boundary, then there's effectively no change due to the propagation speed difference or the different refractive indices. However, when you come in at a larger angle, when the ray comes in at a larger angle, we see significant bending, correct? So just something to pay attention to. So two things become important: the difference in refractive indices and the angle at which the ray comes into the boundary. So those are two things to pay attention to. You could make that angle so extreme so that when you take Snell's law and you try to figure out what the outgoing angle is, let's say I do sine inverse n1 over n2 sine theta 1. If it turns out that n1 is greater than n2 and it's significantly greater, and let's say this sine theta 1 ends up being significantly large, isn't it possible inside of here to get a value greater than 1? Does that mean Snell's law is wrong? Wait a minute, it can't violate the laws of trigonometry, right? So it turns out that eventually it tries to bend so much that the light will not even enter the medium anymore. So if it turns out, if n1 over n2 sine theta 1 is greater than 1, then rays do not traverse the medium. So just one sort of extra warning there. So so when you're close to perpendicular, it looks very much like as if both media were the same. As you start offsetting the direction that the rays are coming in, you get more bending. Eventually there's some limit to where the rays will not traverse the medium, and it does not have to be perfectly parallel, just somewhere along the way based on this algebra. Okay? So now I want to start to talk about simple lenses. Any questions so far? Have you seen this somewhere? Probably. Maybe a while ago. Maybe preparing for some exams somewhere, who knows?